We've done a series of videos on jet engines. The series began several years ago when we constructed a turbojet engine based on an automotive turbocharger that provided the compressor and the turbine functions, and then we designed and built a combustion chamber to provide the heat to drive the engine. It worked. We followed that video with the addition of an afterburner that allows you to increase the thrust of the engine as well as some other interesting things. Now, if you're interested in turbojet engines, you might want to take a look back at those videos because we give a lot of information about the principles, the engineering, the equipment that you need. And once you finish those videos, you probably have enough information to be able to build one of these things yourself. Gas. Now, this turned out to be a very good project. It allowed us to mess around with changing different types of fuels and modifying the combustion chamber to improve the efficiency. And we learned a lot from this, but there's a real negative to it. This engine is very heavy. It weighs about 18 kilograms. And there's an almost equal mass of control and support equipment, the fuel pumps, the oil pumps, the cooling system, the ignition system, the control system, that occupied an entire table below the test stand in order to operate the engine. So great for testing, but not really very portable. So more recently, we tested behind the warehouse here a commercial turbojet engine, this one. And this is a really neat little device. The all-up weight is approximately 3 kilograms, and it actually generates more thrust than this engine because, as you can see, the inducer on the front of the engine is larger. It can pass more air through it. When we tested it, it worked just great and produced a lot of thrust. We then experimented with the addition of an augmenter. Now, an augmenter is not an afterburner. It doesn't use any fuel. It takes advantage of aerodynamic principles to entrain additional air into the exhaust of the engine to enhance the thrust. And I read a number of research papers on the construction of these, and they were very encouraging about the amount of additional thrust we might be able to make with one of these. I designed it, built it, we attached it, we tested it, and it didn't work. Now, I don't think the papers were wrong. I think I probably did something wrong in my analysis and design of the device. It's maybe not sized properly for the particular engines we were testing it on. Maybe the spacing was not optimal. But it's an exciting enough possibility that we probably will circle back to this and we'll do a little bit more investigation on this in the future. In the meantime, though, we moved on to test a third type of engine. This is a pulse jet engine. It was designed by Robert Maddox, and it has an interesting history. This type of engine is about 100 years old, and it was actually used to power the buzz bombs that attacked London during World War II. And they are still currently used on target drones by militaries around the world for one particularly good reason. You see, the tolerances on these types of engines are very high. They're micron level because of the high-speed rotating components. The tolerances on one of these are very low. They're easy to build. If you're a decent welder, you can construct one of these things. And so it's cheap. And if you're going to be shooting something down anyway, it's nice not to spend a lot of money. Downside is they're a little bulky, and they also are very low in terms of their fuel efficiency because they operate at a low compression ratio of about 2 to 1. Nevertheless, they're a lot of fun to operate. They're very loud. It glows red hot when it's operating and produces a substantial amount of thrust. Today, what we're going to be doing is we're going to be demonstrating a pulsed detonation engine. Now, like this engine, it's pulsed. The difference is in the title, detonation, the nature of the burn. In most engines that you're familiar with, whether it's a car engine, motorcycle engine, chainsaw, jet engines, boiler for a steam turbine. The fuel is burned according to a principle called deflagration, with an F, as in Frank. And the way a deflagration operates is that you have a flammable mixture, let's say propane and oxygen, and you initiate a burn, let's say with a spark plug. From the point of that ignition, you begin to get a flame that's spreading outward from that initiation point in an expanding spherical shell that moves through the reactants, chews through them, and produces a lot of energy. What distinguishes a deflagration from a detonation is the velocity at which that flame front moves. If it's subsonic, it's a deflagration. If it's at or above the speed of sound, it's a detonation. Now, the speed of sound is closely related to the mean or average velocity of the particles in a medium, the air molecules that are bouncing around in here and bouncing off of me and the walls. And at room temperature and sea level, that's about 330 meters per second. Now, there's a misunderstanding, or a common misunderstanding, that a detonation will burn the fuel more efficiently than a deflagration. That's not true. You start out with the same reactants, you end up with the same products, in this case carbon dioxide and water, and the amount of energy that is released is the same in both processes. The difference is the nature of how that energy is converted into another form. I'll explain in just a sec. Now, a detonation begins exactly like a deflagration. You start out with a flammable mixture, you initiate the burn, it begins to expand from that initiation point subsonically as a deflagration. But the rate or the movement, the speed, the velocity of that flame front is highly variable. And given the right conditions, right fuels, that flame front can accelerate to the speed of sound and beyond it. And once it reaches the speed of sound, something very interesting happens. You see, you can't transmit an effect or transmit a message from one point to another faster than the messengers are traveling. So when the flame front is expanding at or above the speed of sound, the energy that is normally released during an deflagration, which spreads into the reactions ahead of the flame front, causes them to expand and to warm. And this really isn't useful for generating usable output from the engine. In a detonation, that information or that energy is not able to run ahead of the flame front. It's trapped in the flame front. The propane and the oxygen are just sort of sitting there outside the flame front, completely unaware of what's coming. They don't warm, they don't expand, nothing happens to them until the flame front or the shock wave slams into them. As a result, all of that energy that would normally have been distributed to the fuel and the reactants is trapped in that thin-walled expansion flame front or detonation wave. And so the pressures and the temperatures in that wave skyrocket to thousands of degrees Celsius and thousands of atmospheres. And that pressure is very useful. To give you an idea of why would that be, is the difference in the efficiency between a high compression gasoline engine and a low compression gasoline engine. If you take gasoline vapor, add air to it, a fixed amount of it, place it into a cylinder and then compress it with the piston. If you have a high compression engine, that piston moves a little further up and reduces the amount of volume that that mixture is contained in. When you ignite it, you reach higher peak pressures, and it is those high peak pressures that push the piston down, or in the case of a jet engine, force the gases out of the back, producing the momentum which produces the thrust. We want a detonation because it's less wasteful of the available energy in the burn. Now, if you look at a pulse detonation engine like this one, superficially, it actually is simpler than any of these other engines. You have a pipe, you have oxygen and fuel, and you have an ignition source. The problem is, if we flow oxygen and propane into this engine and ignite it, we're going to end up with a very large blowtorch, very hot and almost no thrust. What we want is a detonation. We want to get that flame front to accelerate to the speed of sound. Now, certain fuels are very good at that. One of the very best is hydrogen and oxygen. If you just have an open tube and it's long enough, eventually that flame front will accelerate along the tube and eventually reach a detonation. Much of the fuel will be wasted in the deflagration, but eventually you'll get a detonation. The problem with hydrogen, though, is it's an inconvenient, very energetic, but inconvenient fuel because it is so light. So even if you have a high-pressure bottle filled with it, it doesn't contain a lot of hydrogen. A much more convenient fuel is propane. At moderate pressures in lightweight tanks, it will remain as a liquid. It's nice and dense, and so you can get a lot in a small volume. So we're going to be using propane, but we still need to get that deflagration to detonation transition to occur, and we want it to occur as early as possible. Now, what the early researchers discovered is that in order to get that flame front to accelerate, they could achieve that by placing obstructions in front of the burn that reflected some of the energy that was being released by the burn back into the flame front, increasing its temperature and increasing its velocity. And what they discovered was an easy technique to do that with is a thing they called a Schlenken spiral, what we call a spring. And they would take this spring and they would actually jam it in the end of the tube all the way to the other end. And what the spring did is the corrugations along the walls would provide enough reflection along the channel so that at some point as the flame front was moving forward along the spring, the flame front would accelerate, reach the speed of sound, and from that point on, you got a shock wave. It works. It definitely works. Now, if you go on YouTube and you take a look at some shorts from some of the researchers over the last decade or so that have been building and working with these engines, you'll see that they look very similar to this. And you'll also see when they operate them that they get these blasts of gas coming out of the end. What they also get is a bunch of sparks, molten metal coming out of the end. What that is the Schlenken spiral being eaten alive inside of the tube. Because when the spiral is in here and the flame front is beginning to accelerate as it moves along here, at some point it reaches supersonic velocities. You now have a shock wave. And so part of this spring is exposed to very high temperature shock waves that are moving past it, and it just chews the thing up. So they don't last very long. Much more recently, they came up with a better method to do this, and it's the one that we're using here, involving what are called aperture plates. Now, you might think that this here is the engine and this is the nozzle. It isn't. The entire tube and this are all the same part of the engine. What this component is here is the detonation initiator. And the way it's constructed with these conflats, just incidentally, if you're not familiar with these things, they're very common in the chemical industry and a high vacuum industry, and they come in a variety of different sizes and thicknesses for different purposes. You can even pick these things up on eBay very inexpensively, $5, $10, $12 each. Pretty good pricing for pretty precise stainless steel manufacturing. In any case, what I did is in the first plate, I bored a little hole and then I threaded it in order to be able to put a spark plug in the end. The second fitting right here looks a little bit thicker, but unlike the other conflats that have this center portion, this actually doesn't have any plate on the inside. It looks like a donut. It's basically just a flange. That provides a lot of room or volume inside here, so when the oxygen and the fuel are flowing in, they have a volume in which to detonate. In front of that, we have the aperture plate. I'll explain how they work in just a sec. The aperture plate will then sit in front of a final conflat here that is welded onto the tube and then acts to mount this whole apparatus with these compression screws on the other side. And then we have little copper gaskets that sit between them and are compressed and will hold back the pressure. This is very, very robust. Now, the way this thing operates is that between pulses, when we're flowing the fuel and the oxygen in here, we almost instantly flood this small chamber here where the gases are being mixed. And then through the aperture plate, the gases, the mixture, can then flow to fill the rest of the tube with a flammable or combustible mixture. When you set off the spark, you get an initiation of a flame front. And what the aperture plate does is all of this material around the outside of the aperture acts as a reflector, sending the energy back into this chamber and creating the detonation. And then what pops through on the other side is a shock wave. The shock wave then plows into the flammable gases, and you get a shock all the way along the length here. These really work well because, number one, they're more robust than these springs. Secondly, you want your detonation to begin as early as possible. You don't want to waste half of the fuel and oxygen in the form of a deflagration before you detonate the end part of it. Unlike the spring or the Schlenken spiral, which requires some length along the spiral before the detonation begins, you don't waste all of this fuel. It begins immediately up here, so it's more efficient. It's more robust. And if you're going to be operating these engines for any prolonged period of time, you're going to need to cool them. And this is much more easily cooled, more easily accessed in order to provide the cooling necessary to keep this at a low temperature. Another feature that you probably see but may not appreciate is these fittings down here. These are called check valves. They're one-way valves that allow fuel or oxygen to travel this way, but they don't allow gases to travel backwards up the tubes. Now, these are very common in things like welding equipment or any place where you're going to be mixing gases that are going to combine, because you don't want, say, the oxygen to retrograde flow into this other line based on pressure differentials and create a combustible mixture that could explode your lines. Very effective, but a problem in this situation because of the pressures involved. You can't get check valves like this that can stand, say, 1,000 atmospheres of impact, which is about what we're talking about here. So the other feature is this small stem that you see that are attaching the check valves to the housing here. These little tubes, I'll show you a close-up here so you can get an idea, are about 10 centimeters long, and they have varying port sizes inside of them. The one that I'm using is actually the one with the smallest port, 1 millimeter in diameter. This serves a couple purposes. One is, because this is stainless steel, it has a very low thermal conductivity. So even when this gets quite hot, it protects the equipment and the tubing up here from the transmission of heat, so you can run this thing longer. More importantly, this very narrow opening creates a pressure drop along the line as the fuel and the oxygen are feeding in here. Because between pulses, the pressures inside of this tube are at 1 atmosphere or maybe even slightly below 1 atmosphere. When the gases pour in, because of that pressure drop, there's no way for the oxygen to go upstream into the propane or the propane to go upstream into the oxygen. So what is in here prior to the pulse is just one gas. It's not a flammable mixture. So when the impact of the pressure wave or the shock wave occurs on the opening here, it can transmit that pressure, but it doesn't propagate the detonation because you don't have a mixture of gases. And because of the very narrow diameter and relatively long length, that detonation wave, as it's moving down through the tube, begins to weaken through surface friction and just over length because of flow resistance. So that weakens the shock wave. Above the check valve and at the end of the tube is this little fitting, the connection. And that connection has about 7 times the volume of the inside of the tube. So when that detonation pulse comes out of the end of this, it tends to spread out, dissipate over a larger area, protecting the check valve. It works. However, we're always into belts and suspenders. And so on the other end of these lines by the tanks are what are called flashback arresters. They're a combination of a check valve and some other features, but basically, if things went completely sideways here, we can't get any of the oxidizer or propane to flow into the opposite tank and create an explosive mixture. You know, safety first. Now, some other features that I just want to explain here. These are the electric solenoids that control the propane and the oxygen. And they are controlled by devices up here. Okay, these are the control boxes. This has a little transformer in it and some switches, one for oxygen, one for propane, and one for everything. And this has a very long extension that allows us to go to a very safe distance back here when we're firing the engine. This is the ignition system. And the reason it's so bulky is because a lot of the papers that I've read based on the design of the ignition and the transition indicated that if you start with a really powerful spark, you get a much more reliable transition to the detonation. Despite everything that I've said, it does help. So what we're running through the spark plug there is 30,000 volts and almost 10 joules per pulse. That's about 100 times the energy that's used in a car or a truck to fire their cylinders, so it's very energetic. In addition, this thing has a rate controller that allows me to pulse this anywhere from 1 pulse per second up to 70 pulses per second. Way in excess of what we can operate the engine at simply because of fuel delivery rates. But it works really well and it's convenient, and we'll be setting this thing up and then I'll be running the engine from a safe zone over here. Couple other things. That's pretty obvious. This here is a load distributor, and distributor in terms of time. You see, when you fire this engine, it's like taking a sledgehammer and slamming it against the front of the engine. And the peak forces can be so high, they could damage the load cell that's going to be measuring the force. In addition, the pulse would be so short that it would be difficult to analyze it. So what happens is we rely on the inertia of the sled that the engine is mounted on, and then this will spread the peak over a longer period of time with a lower peak force and a broader width, making analysis a lot easier. And that's pretty much it. So let's take this thing outside and let's make some noise. All right, we've got everything set up out here, and before we get started, I want to just give you a little bit of a warning, especially for those of you that are wearing headphones. This is incredibly loud. We've done a number of videos where we produce really high levels of sound pressure. This is the loudest thing that I have ever heard, including firing a 12-gauge shotgun next to my head. When this thing fires, it's like getting punched in the chest. Hard. So we'll be damping some of the audio in the video recording, but nevertheless, I just want to make sure that everybody is aware that when we fire this thing, it's going to be very loud. As a matter of fact, we had kind of an interesting thing happen. When we were testing this in an industrial park behind a warehouse about a week ago, my son was located about 100 meters in front of the engine up by the road. And I was located back here and firing the pulse detonation engine. And I fired about 2 or 3 pulses, and then I saw him turn and walk toward the road. So I turned everything off and went over there. It turned out that we got a complaint. And the complaint was not coming from this warehouse or the building back here. A guy in a building on the other side of this warehouse across the road was so concerned about the sound that he came out. And so we had to do a little politics and make nice. But it turns out that he's a fan of the show, and he recommended that when we do this, we do it on a weekend and we do it after hours to minimize the number of people that are around, and that's what we did. So just keep an ear on this because it is very, very loud. Now the first thing I'm going to do is I'm going to turn on the gases. Now the oxygen is going to be turned up to 70 psi, 70 psi. And the propane is going to be turned up to 13 psi. Now that's actually kind of curious because it turns out that that pressure ratio is almost exactly the same as the mixture ratio, or the stoichiometric mixture to get propane to burn. 5 parts of oxygen to 1 part of propane. And what's interesting about that is that almost all the flow resistance in this system comes from these thin tubes that we use between the check valves and the engine itself. And the flow resistance in those is not linear. In other words, if you double the pressure, you don't double the fuel flow. So even though we're set up at this ratio, I suspect we're still not dialed in to the optimal mixture. So there may be some more tweaking that we're going to have to perform when we get time at the right time of day and the right time of the week to be able to study this a little bit further. But we're going to demonstrate this at those pressure levels. Now, I'm going to run this at 1 pulse per second, or 1 hertz. And so I'm going to start up the electrical system, then I'm going to go over there in order to control the pressure and the gas flows from a safe position. So are you ready over there?
Yeah, if you can just do one little test with your hand, just make sure it's working.
You ready?
Yep. Yep, it's working. You're all good.
All right, here we go. 1 hertz. You set?
Yep.
All right, oxygen, gas.
Thank God.
Pretty impressive, huh? Just to give you an idea of how much power was involved in that reaction, the internal volume of the engine is a little less than 1 liter, and so the total mass of oxygen and propane together is 1 gram for each one of those explosions. 1 gram of propellant. Thing is potent. All right, you want to try it at 3 hertz?
Yep, and I think this is still working. By the way, guys, this software setup thing is really annoying. So that's why we had to do this a few times to make sure that we get the right data. So bear with us.
All right.
But yeah, I'm ready.
Okay. All right. So now we're going to try it at 3 hertz. Are you ready?
Yep, good. I got it. I got it. I got it.
You gotta love this. All right, now I want to do one additional experiment with this. Normally, jet engines don't use nozzles or bell nozzles, expansion nozzles. But rocket engines do, because the way a rocket engine works is it produces a high pressure chamber containing the gas. And then the throat narrows it down so that that high pressure gas is limited to the speed of sound. And in the bell, the expanding bell from the rocket engine, the gases are able to expand and convert that pressure into velocity. I don't know how that would work with a system that has a high pressure in it, but is already exhausting gases at supersonic or hypersonic velocities. Does it help or doesn't it? So I'm going to attach this to the end of this, and we're going to run it again. All right, we're going to try this out at 1 hertz. Let's try 2 hertz. We'll see what happens here. All right, you want to run a test?
Well, you don't want to do 1 hertz, so it's exactly the same.
All right, 1 hertz.
Yeah.
Okay, you want to test this first?
No, because it adds to the...
Okay, so am I good to go?
Should be, yeah.
Okay.
I'll stop you if I don't think so.
All right. All right, oxygen on.
I didn't like that.
I didn't either.
That was way more violent. I have the headphones on, but that you can feel it in your chest. That's way more violent.
We don't have the data right yet, but I'm pretty sure this nozzle does make a big difference. I suspect the forces were much greater.
They were. I'm seeing it now. They were.
Yeah. Yeah. Pretty cool. What you are now looking at are the three graphs that represent the three test runs. The graph on the left is the 1 Hz test with a straight tube. The middle graph displays the 3 Hz run with the straight tube, and the right graph shows another 1 Hz run with the added nozzle. For those of you interested in the numbers, we placed a link in the description below the video to allow you to download the tabular data that generated these three graphs. One feature you can see in the right-hand graph is the small peaks between the large pulses. This represents a small bounce that occurs between the more powerful pulses because our test sled has minimal damping. Now, something common to all the tests is the thrust drop-off with each successive pulse. This is likely due to fuel and oxygen starvation caused by flow limitations through the small diameter fittings between the check valves and the engine. This, however, is an easy fix. By increasing the internal diameter and using sharp angle changes in these tubes to redirect the shock waves back toward the engine, or a Tesla valve, which itself could be the subject of an interesting video. Now, comparing the two 1 Hz tests in the left and right graphs, we see significantly higher thrust when the nozzle is added. There are two possible explanations for this. The first is that the nozzle is acting as expected. Just like in a rocket nozzle, the cone redirects the pressurized exhaust gases backward as they exit the tube and expand. The second possibility is that the nozzle effectively increases the volume of the engine and the amount of propellant that is detonated. I favor the first explanation because the second, third, and fourth pulses with the nozzle are more powerful than the second, third, and fourth pulses without the nozzle. If propellant starvation is causing the decline, then increasing the engine volume when it isn't even full shouldn't make a difference. In fact, the subsequent pulses with the nozzle are even more powerful than the most powerful pulse without the nozzle. After analyzing these results, I was shocked. The metric used to determine the performance of a rocket engine and its propellants is called the specific impulse. This is how it works. If a rocket burns 1 gram of propellant and generates 100 grams of thrust for 1 second, the specific impulse is 100. If it generates 200 grams of thrust for 1 second, the specific impulse is 200. If it generates 100 grams of thrust but maintains this for 2 full seconds, the specific impulse is still 200. If it generates 100 grams of thrust for half a second, the specific impulse is 50, and so on. The large pulses in the 1 Hz straight tube, no nozzle, show a specific impulse of 514. With the nozzle, the specific impulse increases to 584. For comparison, SpaceX's Raptor 3 engine, probably the most advanced rocket engine in existence, has a specific impulse of 350. This engine, which is a first attempt and not optimized in its design and certainly not with its propellant ratios, is 60% more efficient, and it doesn't even need turbo pumps. This is huge. And so we are going to reach out to Elon, and if anyone out there watching this video can help facilitate this process, we'd appreciate it. Now, undoubtedly, some of the engineers at SpaceX are aware of pulse detonation engines, but seeing this real-world demonstration of its performance may generate some additional attention. These engines have a very low average thrust, but an extremely low fuel consumption. Once orbit has been achieved, and as a final stage on, say, a Starship, such an engine could reduce the necessary propellant, allowing for more payload. Or with the same amount of propellant, the ship could achieve higher terminal velocities, shaving months off of a trip to Mars. Stay tuned. Now, what's interesting about this construction is very simple, and it has the potential to improve the performance of all types of momentum engines that send gas out of the back, jet engines, even rocket engines. There is a downside with the pulse nature of this engine, and that is the duty cycle, or the effective average thrust. Because even if this thing is operating at, say, 100 hertz, the pulse duration is so short that the actual fraction of time that the engine is producing thrust may only be 2 or 3%. There is another type of detonation engine that has been in the news recently. It's called the rotating detonation engine. And if you're not familiar with it, the rotation is not the engine. It doesn't rotate. What rotates is the detonation wave. It's constructed by taking two concentric cylinders, one slightly smaller than the other, producing an annular gap between the two cylinders. Fuel and propellant are pushed in from the back, and then a detonation wave is set up in that annular gap, which rotates or moves around the gap at hundreds of thousands of RPM. And it's not like a rocket engine in terms of all the fuel is being burned all the time. It still is a thin detonation wave that's moving through it. So it's more like a pulse detonation engine that is operating at thousands of hertz. And as a result, would have a much higher average thrust for a given size engine and may potentially be even more useful. It's probably slightly less efficient for fuel because that narrow gap has much more resistance to flow or the movement of the detonation through than this much larger tube. But that increase in effective frequency would be a huge, overwhelming advantage in that kind of an engine. And I'm working on that right now. So if you're interested in this kind of topic, we're going to continue on over time and try a few different shaped nozzles as well. But what I would ask you is, if you've enjoyed this video, please consider subscribing, because the more subscribers we have, the more it pushes YouTube to distribute our videos to a much larger audience. That helps the channel. And with the recent decreases in remuneration from YouTube from ad revenue, what has kept us viable has been the support from the Patreon community that provides the additional funding to support the facility, the equipment that we use. Everything that is given to that community or to us through that community comes right back into the channel. So if you think you can't afford it, take a look at the link below the video in the description and visit it, because that kind of a support will allow us to continue to do projects, larger projects, and continue to make us viable into the future. In any case, I want to thank you all for watching. Please stay safe, have fun, and we'll see you soon. Oh, yeah. Yeah.
So, well, actually, if you want to see, so the last one that you just did was this one, peak compression, negative, obviously,
Yeah, 16.
switch it,
Yeah.
so 16, versus, and you'll see.
Wow.
Yeah, big difference.